Intel and QuTech, a collaboration between Delft University of Technology and the Netherlands Organization for Applied Scientific Research, published key findings in quantum research to address the interconnect bottleneck that exists between quantum chips that sit in cryogenic dilution refrigerators and the complex room temperature electronics that control the qubits. The innovations were covered in the journal Nature and mark an important milestone in addressing one of the biggest challenges to quantum scalability with Intel's cryogenic controller chip Horse Ridge. A key bottleneck for quantum computing lies between the quantum chip stored in low cryogenic temperatures in dilution refrigerator and room temperature control electronics that control the qubits. Getting the control electronics to operate at high fidelity at cryogenic temperatures is key to overcoming what is referred to as the interconnect or wiring bottleneck. Intel took the first step to address this challenge when it introduced Horse Ridge, a cryogenic control chip for qubits built using Intel's 22nm FinFET low-power technology. A second generation of the chip was introduced last year. Horse Ridge brings key control functions for quantum computer operation into the cryogenic refrigerator as close as possible to the qubits themselves to streamline the complexity of control wiring for quantum systems. This latest research successfully demonstrates results from randomized benchmarking that show a commercial CMOS-based cryo controller achieving coherent control of a 2-qubit processor at the same levels of fidelity, 99.7%, as room temperature electronics. This marks a key research milestone in the field of cryoelectronics for quantum computing. Intel and QuTech successfully demonstrated frequency multiplexing by using the same cable to control 2 qubits. This is an important proof of concept because today each qubit is individually controlled by its own cable, an approach that is not scalable as qubit counts increase. Horse Ridge aims to solve that limitation by leveraging multiplexing to reduce the number of radio frequency cables needed for qubit control. The research team demonstrated the programmability of the controller by running a 2-qubit algorithm called the Deuce-Jozsa algorithm, which is more efficient on a quantum computer than a traditional computer. The research results, verified by randomized benchmarking, validate the original promise of Horse Ridge as a highly integrated and scalable solution for simplifying quantum control electronics and prove that the technology can be directly applied to multi-qubit algorithms and noisy intermediate-scale quantum devices. With continuing research in this field, it may be possible to fully integrate the controller chip and the qubits on the same die. They are all fabricated in silicon or package, paving the path for quantum scalability.